In the previous lectures, we talked about drawing Lewis structure and drawing bond line structure for organic molecules. In this video, I'm going to review a few concepts from general chemistry. Again, if you don't remember these concepts, I strongly suggest you to get back to your Gen Chem notes, look up the definitions. I'm going to review all of them here. Hopefully, after this review, you can remember all the concepts from your Gen Chem book. Let's start with the concept of electronegativity. Electronegativity shows how strongly an atom can attract the bonding electrons toward itself. So if you look at the table 1.1, we have a trend for electronegativity in the periodic table, meaning that moving from left to right and bottom to top, electronegativity value increases. That means fluorine has the highest value, so it is the most electronegative atom in the periodic table. If you go away from fluorine, you are losing electronegativity. So consider a bond like carbon nitrogen bond. If you look at the electronegativity value for nitrogen, the value for that is 3, and for carbon it is 2.5. So nitrogen is more electronegative than carbon. That means nitrogen pulls these bonding electrons toward itself more than carbon. So you can also easily calculate the electronegativity difference between these two atoms. So nitrogen is 3 minus 2.5 gives you 0.5. This is the electronegativity difference between carbon and nitrogen in CN bond. Based on the electronegativity difference in atoms, we can have different types of bonds: covalent bond or nonpolar covalent bond, polar covalent bond, or ionic bond. Covalent bond is the result of sharing unpaired electrons between two atoms. If the electronegativity difference between those atoms is less than 0.5, we have covalent bond or nonpolar covalent bond. If that difference is between 0.5 to 1.7, we have polar covalent bond. Now consider the structure of a chlorine molecule. Each chlorine has an unshared electron in its valence shell, so they will share that unshared electron to one another to make a single bond. Now if we calculate the electronegativity difference between two chlorines, both chlorines have the same electronegativity value, so the difference would be 0. This number is less than 0.5, so Cl-Cl bond is a non-polar covalent bond. Now if you consider the bonding in hydrogen chloride, HCl, hydrogen has an unshared electron, chlorine also has an unshared electron. They will share those electrons to one another to make a single bond. If we calculate the electronegativity difference between hydrogen and chlorine, that would be 0.9, which falls within this range. So HCl bond is a polar covalent bond. Please consider that chlorine is more electronegative than hydrogen. Therefore, it pulls the electron density toward itself. So it wants the electrons more. Therefore, electrons not evenly shared between hydrogen and chlorine. In ionic bonding, electrons are not shared, and electrons are completely transferred between two atoms. Usually, ionic bonding is formed between metals and nonmetal. For example, here we have sodium chloride. Sodium has a single electron in its valence shell. It will completely transfer it to chlorine to make a positively charged ion, and chlorine accepts that single electron to make a negatively charged ion. The electrostatic attraction between these ions, we call that ionic bonding. This is the summary of what I just talked about. So if the electronegativity difference between two atoms is less than 0.5, we have nonpolar covalent bond. An example of that is carbon-carbon and carbon-hydrogen bond. We have a lot of them in organic molecules, so we consider them as nonpolar covalent bond. And if the cutoff is between 0.5 to 1.7, we have polar covalent bonds. Some examples, NH bond and CO bond, they are polar covalent bonds. And if the electronegativity difference is more than 1.7, we have an ionic bond. Example that we just talked about is sodium chloride. So actually there is no bond between them, it's just the electrostatic attraction between opposite charges. So we have an exceptions here. Carbon-lithium bond, if we calculate the electronegativity difference between them, between carbon and lithium, it's going to be 1.5. So it's basically falls in the cutoff of this region. So we are allowed actually to draw the carbon-lithium bond as polar covalent or as ionic bond. So you're going to see that bond later on in organic chemistry. Electronegativity tells us how strongly an atom can pulse bonding electrons toward itself. And this leads us to the concept of induction. Consider carbon-oxygen bond. We know that oxygen is more electronegative than carbon, and this bond is a polar covalent bond. Therefore, oxygen will pulse the bonding electrons toward itself, and to show this movement, we are using an arrow with a little slash on a tail on carbon and head on oxygen. We can also use another way to show this. As I said, oxygen is more electronegative, so it pulls the bonding electrons toward itself, and electrons are negatively charged. Therefore, oxygen gets the partial negative charge on it. However, carbon would experience less electron density around itself, so it gets the partial positive charge. This withdrawal electrons toward an electronegative atom is called induction, which is a very important concept for us, especially while we are discussing organic reactions, to know where the reactive electrons are located. Practice problem. So in this practice problem, I want you to be able to identify the polar covalent bonds and draw partial charges, positive or negative, on an appropriate atom. So let's look at the first molecule. In this molecule, we have carbon-hydrogen bonds, carbon-carbon bonds, and one carbon-oxygen bond. So we already talked about it. Carbon-hydrogen and carbon-carbon bonds, both of them are nonpolar, so we ignore them. And the remaining one, which is carbon-oxygen bond, we know that it's a polar covalent bond, and oxygen is more electronegative than carbon. Therefore, it pulls the bonding electrons toward itself. And oxygen would get the partial negative on it, and carbon would be partially positive. Now, if you look at the second molecule, we have carbon-hydrogen bonds in it, carbon-magnesium and magnesium-bromine bond. So carbon-hydrogen bond, again, it's nonpolar, we ignore that. Carbon-magnesium bond, carbon is more electronegative than magnesium, therefore carbon would get the partial negative charge on it, and magnesium is partial positive. And arrow should be towards carbon. In magnesium-bromine bond, again, bromine is more electronegative than magnesium, so bromine would get the negative charge and magnesium would get the positive charge. So therefore, magnesium will be even more positive. than before, so it would get a larger partial positive charge, and the arrow should be towards bromine. Now, if you have a molecule with more than one polar bond, we want to know where would be the molecular dipole moment in the molecule. So to identify that, the very first thing is to find the geometry of the molecule first. The geometry here is very important. We are going to talk about the geometry in the next videos. And the second one is finding the polar bonds and their vectors. So if you consider the structure of dichloromethane, dichloromethane is in a tetrahedral geometry, and we have two polar bonds in the molecule. Chlorine is more electronegative than carbon, so both of these arrows are going towards the chlorine. Now, to find the molecular dipole moment for dichloromethane, what you need to do is just to take the vector sum of the individual dipole moments in the molecule, and doing that, that would be the direction of the sum of these vectors. Now, sometimes the molecule has more than one polar bond, but the overall molecule is non-polar. So if you consider the structure of CO2, we have two polar bonds, two CO bonds here, and oxygen is more electronegative than carbon, so both of these arrows are going toward the oxygen. Now, electrons are going towards the oxygen with the same strength and in the opposite directions, because both oxygens have the same electronegativity, so the strength is the same but in opposite direction, causing that these vectors cancel out each other, and the overall molecule would have a zero dipole moment. So the whole molecule is non-polar here.